So, as I've said a few times now, we spent a lot of time with regular languages. We spent a medium amount of time with context-free languages relative to the size of lot. It's very medium, even small. And now we're leaving context-free languages and we're moving into kind of the everything else category. And the good news is, having seen stuff in regular languages to great detail and then in context-free languages a little bit less detail, this next step we'll also do in a little bit less detail, but it's going to be a little bit more challenging, a little bit more interesting. So let's very quickly review where we came from and where we're going. We started with regular languages, and of course remember that a language, we're always just talking about a set of strings, right? And we represented our regular languages as regular expressions. We found regular grammars that could generate our regular languages, and we had a couple of kind of things that I sometimes called computers. I mean, they are computers, they're very simple computers. Our DFAs and NFAs, which we could use to kind of run a program almost to check, right? Is this string in my language? So that was the regular language, and we have this kind of, we could call this a Venn diagram that has the set of regular languages in there, because as we know, there's some languages that are not regular. So continuing on with our Venn diagrams, we've got the regular languages, but then we've got some languages in here that are not regular, right? And to prove that, there was the Pumpinglemma for regular languages, which we could use to do a proof by contradiction to prove that there are actually some languages that are not regular, because the Pumpinglemma was a property that told us something about regular languages, and if we found a language didn't have that property, then it had to be out here, right? It had to be not a regular language. And of course, we called the languages that are in this region the context-free languages. This is a superset of the regular languages. Again, think of this as a Venn diagram, right? And all of our regular languages are definitely inside context-free, but there are some languages that are context-free that are not regular, right? So a language that's right here, for example, context-free, not regular. A language that's right here, regular and context-free. And then we talked about how to generate context-free languages using a context-free grammar. And we also talked about a single machine, our PDA, which again is a kind of simplistic computer, right? That could tell you whether a language was in fact, whether a string was in my language, right? So the PDA tells me, is this string in my language? Right? And the interesting difference about the PDA from our NFAs and DFAs was we had a little bit of memory, right? It wasn't a great quality of memory because it was a stack, and we could only kind of see one thing at a time that was on the stack, but still, it was amazing because, if we had a language like a to the n, b to the n, such that n is a natural number, right? Our favorite language that is not regular but is context-free, we could look at strings in this language using a PDA to determine look at strings to determine whether they were in the language, right? Whereas you just can't do that with an NFA or a DFA. So that's interesting and cool. That was our context-free languages. And punchline, you kind of knew this was coming. I probably said it in an earlier slide in this lecture, right? There are languages that are not context-free, right? And this is sort of the everything else. Perhaps this outer circle in our Venn diagram really shouldn't be a circle, but it should just be the universe of everything else, right? But we've got, here's a language right here that is not context-free and not regular, as opposed to a language in here which is both regular and context-free, right? Or something in here, context-free, not regular, but also kind of in this everything else category too. Now, just like we proved that some languages are not regular by using something we knew about regular languages, right? The Pumpinglemma, which now we're going to call the Pumpinglemma for regular languages. We used to just call it the Pumpinglemma. There is, in fact, a Pumpinglemma for context-free languages that will tell us something about context-free languages. And if we have a language and we assume it's context-free and we do a proof very similar to the proof for to prove that a language wasn't regular, we can show the language is not context-free if it doesn't meet certain criteria. So just as a reminder, here's our Pumpinglemma that we used for regular languages, and now we're going to call this the Pumpinglemma for regular languages. And we said, let L be an infinite regular language, and of course it has to be infinite, right? If you have a finite language, remember, this is really important. All finite languages are regular, right? Because if you think about it, if it's finite, then it just has a finite set of strings. Let's suppose there's 10,000 strings, right? And the first string is AB, and the second string is BCDA, and the third string is QED, and whatever. You can represent that using a regular expression that just has 10,000 different things in there. Did I say it was 10,000? A set of 10,000 things? So all finite languages are regular, okay? And what we really care about is infinite languages. We're looking to try and prove something is not regular. So it we say, suppose we have an infinite regular language, and then we said there exists some value m, so that if we have any string that's in the language where the length of the string is at least m characters long, then we can split S into this subpieces X, Y, and Z. Remember all this? Where we said Y is definitely not the empty string. And the length of the XY part of this substring is less than or equal to M. And we can pump it, right? And how do we pump it? We can take 0 or 1 or 2 or 3 copies of Y. And that will still be in our language, right? So this was the Pumpinglemma for regular languages. And here's the Pumpinglemma for context-free languages. It's written in such a way that you can kind of see the differences here, right? So of course our language has to be an infinite context-free language, because if it weren't infinite, we know for sure it would be just regular, which means it's context-free. Now, instead of splitting S into XYZ, we are now splitting S into more pieces, right? U, V, W, X, Y. And this kind of makes sense because before, with the Pumpinglemma, we could pick any one piece and pump it, and our string would stay normal, or would stay regular, right? Now what we're going to do, I mean, here's again, the punchline here, is that instead of just pumping one piece, we're going to be able to pump two. So, and this should make sense to you, right? Because this is with our stack that we have for our PDA, for example. You can kind of match two pieces of a string and pump them infinitely long, and it will still be context-free. It'll still be something that your PDA could recognize, right? And so if you look at this page here, the Pumpinglemma for context-free languages very, very similar to the Pumpinglemma for regular languages, except we're going to split our language into UVWXY, right? And so our string, we're splitting our string into UVWXY, right? So, and the important thing is the VX part is not lambda, or the length of the VX part squished together is greater than or equal to 1, right? So this is very similar to this rule here. And if we take the VWX part, so that's this middle part, ignoring you know, the stuff at the very beginning and the stuff at the very end, that has to be less than or equal to m, right? Whereas before, the length of that, whereas before we had the length of xy had to be less than or equal to m. And then there's this last piece that says it can be pumped. Now, we're not going to do a lot of proofs using the pumping lemma for context-free languages. What I will tell you is, of course, it works just like the pumping lemma for regular languages. It really is, you know, the proofs are almost absolutely identical. And if you know how to, if you feel competent with proving that a language is not regular, using the pumping lemma for regular languages, you can be pretty confident that you're going to be able to do something very similar with the pumping lemma for context-free languages. The outline is going to be exactly the same. So what I'm going to do, because this proof is kind of long and intense, these kinds of proofs, is I've set that up as a completely separate lecture. So I'm going to go on and not give you an example of a pumping lemma for context-free languages right now. But after you finish watching this lecture, the next piece that you'll watch is the pumping lemma for context-free languages example. And that way, when you want to see an example, you can watch the example and you don't have to kind of hunt through these slides to find it, or hunt through this lecture. But for now, I'm going to keep going and talking about one of the most fun things in here, which is talking about a computer for non-context-free languages, right? A machine, some sort of a machine. And remember, I mean, we've already said, okay, we have a machine that will recognize regular languages, right? We have two, actually, a DFA and an NFA. Those are, you know, they're kind of small computers that recognize regular languages. You give them a string, you give them, and it will tell you this string is in the language or this string is not in the language. And of course we continued and we came up with a new kind of machine for context-free languages, which was the PDA. And of course anything that you can recognize with a DFA or an NFA you can also recognize with a PDA, but the PDA was a little bit more powerful than the DFA and the NFA, and we got that power from the stack. Right? We added a stack to our NFA and suddenly we just had so much more power. We had a little bit of memory, right? And memory always helps. So the machine for everything in here, which is actually anything you can program, this really is a machine for everything else, is called a Turing machine. And like I said, the Turing machine really is for anything else, everything else. Anything that you can program using a Turing machine. It will be a major pain to do it on a Turing machine. And I have here, you know, your input-output isn't going to be the same because a Turing machine really can only write symbols. It can't give you pictures. It can't give you sounds. But of course, we know that you could represent anything in binary. So we'll assume that whatever the Turing machine outputs, we could translate that into a picture, or we could take a picture, translate it into binary representation of that picture, and put it into our Turing machine as input. So really, the Turing machine is equivalent to the PC, the Linux machine, the Mac on your desk. Okay? We are now actually going to talk about a computer that is a model for every other kind of computer, right? And here's where it gets fun, because remember, I said that there are programs that cannot be written. Right? And if a Turing machine is equivalent to any other computer, and we're not going to prove that, but trust me on it, then if we can prove that a program can't be written on a Turing machine, then we can prove that program can't be written anywhere. And we are very, very close to proving that there's a program that cannot be written. That's 2 lectures from now, so get ready. Very exciting. It really is. It's good. It's cool. You will like the proof. It will be you may have to watch the video a couple times because it's going to be one of those what did I just see proofs, but it's a good proof. So here's what a Turing machine looks like. In fact, there are a bunch of different models that you can have for a Turing machine. This is just one way you can think of a Turing machine. You can think of it a bunch of different ways, but this is the way that we're going to do it for this class. Okay, so a Turing machine kind of has an NFA inside of it. That's the CPU. So inside of there's some circles and arrows that are hidden in there. Okay. It's a little bit different from an NFA, a little bit different than a PDA, but we'll get there. And instead of having a stack for our memory like we have in a PDA, now we get an infinitely long piece of tape, we call it, right? An infinitely long piece of paper that has a bunch of cells. So here's, there's one cell and there's another cell, and we can write one thing in each of these cells. Okay, and each Turing machine instruction, which is in the CPU, is going to tell us when you can run that instruction, right? Based on what's the current state, right? What circle am I in right now, and what symbol am I pointing to by the tape head? So it's just like the way we did it with a PDA, where we said what's at the top of my stack and what letter do I see? Well, now we're going to kind of do something very similar and say what is my tape head, right? this arrow out of the CPU pointing at, right? And it's also going to tell us what to do, how to run the instruction, right? What should we write on the tape? How should we move the tape head? And how do we transition to our next circle, our next state in here? So let me go into a little bit more detail about this. So, this is what we had before, and now I'm just going to kind of explain it, okay? So the first thing a Turing machine instruction has is what's the current machine state. So that's just like we're used to. I am in state I, right? And then there is the symbol written on the tape. And notice I've tried to color code this for this slide. So if I am in state I, and on the tape head is pointing to this letter A. So let's just circle the A. So if I'm pointing at the A, then what I should do, this is what I write on the tape is purple, right? Then replace that A with the letter B. So in fact, if I want to leave the A alone, I just have to put an A there again. And then there's the direction to move the tape head, right? So if I see the letter A, replace it, overwrite it with the letter B, or I could overwrite it with an A again if I wanted, and then move the tape head in this direction, and the possible moves are left, right, and stay put. Don't move the tape head, right? And then finally, where do I transition to? What's my next state? J, right? So that's what this kind of notation has, right? The current state of my machine is I, and if the symbol in the current tape cell is A, then replace that A with a B in the current tape cell and move in the direction D by just one cell and switch states, transition to state J. Let me say this again. If you go to a party and you start talking to people about Turing machines, you may discover that the Turing machine model that we used is different from the Turing machine model that they used. And if they say, no, that's not possible, you say, oh yes, of course it is. There are multiple different models for Turing machines, and I just have one and you have one, and they are in fact equivalent. So let's talk about some of the things we assume and some of the rules about Turing machines. We're going to assume that the input string, when we get started, the input string is written on the tape, and very important, all the other tape cells contain lambda. So if we're trying to test the string ABC, then our tape, remember it's infinitely long, right? Made up of a bunch of these little cells. And A, B, and C are each in cells, and it goes out infinitely long, and every other cell has a lambda in it. Okay? Furthermore, when we start to run our Turing machine, the tape head is going to be pointing at the leftmost symbol in the string. So in this case, we're going to start with our tape head. If my string is ABC, we'll start with my tape head pointing at that A. Okay? There is exactly one start state, just like before. But now we have one special state called a halt state, and we're going to put a big H on that state. Okay, we'll label it with an H. Right? And the Turing machine stops computing. Right? With our NFAs, we stopped if we couldn't make any more transitions, right? And then we checked whether we were at an accept state. The Turing machine is going to stop if under two circumstances, right? Either if there's no valid move to make, just like in an NFA, right? We kind of fall off it. Or if it arrives at the halt state. If you get to the halt state, you win. You're done. You halt, right? And that's what I just said. A string is accepted by the Turing machine if and only if the machine enters the halt state. So if your first move is to go to the halt state, you win. And if you never make it to the halt state, then the string is not accepted by the Turing machine. So I think this might be more clear if I show you an example. So here's a Turing machine for A star, B star. And of course, I've described the language as a regular expression, so you know this is actually a regular language. But it's interesting anyway to kind of look at this example because it's a nice simple example, right? And it looks in many ways similar to our PDAs and our NFAs. So let me just shrink this slide just a little bit, and let's try a couple of example strings. So let's first try the string AAAB, which of course is in my language, right? And so what's going to happen is we're going to start with a tape that looks this. And it goes infinitely long in each direction. And I'm not going to write in the lambdas, just assume that a blank space on a tape is a lambda. Okay? And when we start running our program, we have the tape head pointing at the first character in our string. Okay? And so let's see, we start at state 1. Right? So we're in state 1. And at state 1, it tells us if you see the letter A on the tape head, well, we do, if the tape head is pointing to A, then replace it with an A and move the tape head one cell to the right. And that's our only option right now, right? Because if we look at this one, this says if you see a B on the tape head, and this one said if the tape head is pointing to a B, sorry. And this one said if the tape head is pointing to a lambda. This is not a free jump like in an NFA. This is if the tape head is pointing to a lambda. So the only transition we can take is this one. And again, it says if we're pointing to an A, which we are, replace it with an A, so that just means leave it alone, and move the tape head to the right. So what we're going to do is we will move the tape head one space to the right. Okay? And we're still in state 1, right? And we're in state 1, we see another A, so we're going to take this transition again. We're going to see the A, we're going to replace it with an A. So, I mean, strictly speaking, we could say, oh, I crossed out that A and overwrote it with an A. I'm crossing out this A and I'm overwriting it with an A. Usually I just say I'm leaving it alone. But so we overwrote it, and then it tells us to, so overwrite with another A and move one step to the right. So we will do that again, and we move the tape head to the right. And of course we'll take that same transition one more time, replacing that A with another A, and moving the tape head to the right by 1. So now we are still at state 1, but we have something slightly different because now the tape head is pointing at the letter B, the symbol B, right? We look, we can't take this transition, we can't take this transition, but fortunately we have this one, right? If I see a B, I do replace it with a B and take one step to the right, move the tape head one step to the right. So I'm going to take my B, replace it with a B, and then move the tape head one step to the right. Okay. So now we've transitioned to state 2, right? In state 2, it says, well, if you see a B, I see a lambda, but fortunately there's this one. So if you see a lambda, replace it with a lambda. So I could cross that out and put a blank in there again. Stay put, and magic, you have arrived at halt. Okay? So I got to halt. That means the string AAAB is in my language. Done. I'm done. Okay? Let's try another couple of examples. I'll do this one in red. Suppose I want to check whether the string lambda is in my language. So I write lambda on the tape. We're using just a blank to represent lambda. I point the tape head at my string. And, right, tape head goes to the first symbol in my string. In this case, it's lambda, so we just kind of leave it wherever because they're all lambdas, they're all blank. And we get to start. We're at state 1. The only transition we can follow is this one, right? It says if we see a lambda, then replace it with a lambda, stay put, and go to halt, and magic, we're done, right? And that makes sense because, of course, our language is A star, B star up here, right? Which does include the symbol lambda, right? So let's try one more example. Let's try something that's not in my language, right? Why don't we try the string ABA. That's not in A star, B star, right? So we're trying the string ABA. We start the tape head at the first symbol in the string. And we are at state 1, and it says if you see an A, replace it with an A and move the tape head one to the right. So, oops. So we will leave that A alone. I could also cross it out and write an A again and move the tape head to the right. And we also stay at state 1, right? That was our transition loop. So we're at state 1. And now the tape head's pointing to a B. The only B that I see that we can follow is this one, this transition. So if you see a B, replace it with a B, move the tape head to the right once. So we're going to move the tape head to the right, and now we are at state 2. And at state 2, there's 2 out transitions from state 2. One says if you see a B on the tape, the other says if you see a lambda on the tape. Well, my tape head's pointing at the letter A, right, at the symbol A. I don't see a B, I don't see a lambda. There is nowhere I can go, so that's it, we're done. We did not accept. The string ABA is not in my language. Okay, we had deterministic finite automata, right, DFAs. And we had NFAs, non-deterministic finite automata. And with our PDAs, our push-down automata, we said some of them were deterministic and some of them were non-deterministic. Here's the definition of determinism for a Turing machine. Right? And the definition for deterministic with a Turing machine is very similar to that of a PDA. Right? A Turing machine, if it has at least 2 instructions with the same state and input letter, which means basically you have 2 transitions you can choose between, right? Then it's non-deterministic. Otherwise, it's deterministic. So the PDA we saw on, or sorry, excuse me, the Turing machine we saw on the previous slide for A star B star was deterministic because at any particular state there was only one choice of what to do. But you could imagine that we could have something that looked like this, which said, you know, if you see, if you are at state 1 and you see an A on the tape, you can replace it with an A and move the tape head to the right. Or if you see an A on the tape, you could replace it with an A and stay put. And this would be part of a non-deterministic Turing machine, just like a non-deterministic PDA, because you actually have a choice, right? And so you can choose which path to follow. And of course, same as with an NFA, same as with a PDA, if there is any path that you can choose that will take you to the halt state, then you accept. So here's another example of a Turing machine. This is a Turing machine that adds 2 to a unary number. Of course, we know what binary numbers are, right? Binary numbers are base 2. A unary number is in base 1. So the number 4 in base 10 is the same as 1111 in base 1. So if I want to represent the number 6, it's 1, 2, 3, 4, 5, 6 in base 1. All right, you get it? Makes sense. So here's a Turing machine that does that, and we want to add 2 to this number, right? And of course, to add 2 to any unary number, all you do is you add 2 more 1s. So if this is up here, I have the number 6, right? And I could make that the number 8 by adding 2 more 1s, right? And I can make this number 4 that's written down here, I could turn that into a 6, presto changeo, by adding 2 more 1s. Now it's 6 in base 1. Okay? So if you think about it, what do we need to do if we're starting at the front of the string? We need to move to the end of the string, making sure everything that we see is a 1, and then when we get to the end, we add a couple more 1s. Right? So let me shrink this a little bit. So we have a little bit of room. Actually, I can make this big. And let's do a few sample strings to see how we add 2 to a unary number on a Turing machine. So here's an example. Let's try adding 2 to the number 3. So we've got the number 1, 2, 3. We start the tape head here. Blank symbol I'm going to leave is just going to be a lambda, right? So maybe I'll write them in this time. So you just remember every single spot on the tape that does not have something in it is going to be a lambda. Okay? So we get to the start state, and this says if you see a 1 on the tape, replace it with a 1, go right. This is what we said, right? So we see a 1, so we're going to move the tape head to the right. And then we see another 1, so we move the tape head to the right. Of course, we see another 1, we replace it with a 1, move the tape head to the right. So we keep doing that. And what does it say here? I see a 1, replace it with a 1, move to the right, so we move the tape head again. Ooh, and now I see a lambda. And so now I can't take this loop anymore. I have to take this transition, right? And this transition says, if I see a lambda, replace it with a lambda and move it to the left, and move to the left, right? So now I got to move back to the left. And we could, of course, have just added a couple of 1s at the end. This is an example from the book, and the book wants to end for no good reason. It's totally fine to do so, totally fine not to do so. But something that they didn't write is that they're going to end with the tape head pointing at the start of your unary number. So what they're going to do now is, if you see a 1, replace it with a 1 and go left. So we're just going to go left. So we see a 1, we replace it with a 1, and we move left, and we do that again, and we do that again, until we get to here. So now my tape head is here, right? And we're in state 1, and we see a lambda, and it says, if you see a lambda, replace it with a 1 and go left. So goodbye lambda, now you are a 1, and the tape head has moved over by 1, and we are now transitioned to state 2. And if you're at state 2 and you see a lambda, which we do, replace it with a 1 and stay put. So we're going to place it with a 1 and stay put, and you can see that I started with the number 3, now I have the number 5, and bonus, I'm showing you the number 5, and I've put the tape head pointing at the beginning of my string. Not essential. Book should have told you that that was part of the instructions for this particular Turing machine, but it's fine. Okay, so let's try something else. What if we have the string, and I'm not going to write in the lambdas anymore. Let's pick a string that doesn't work, right? What if we have the string 1011, right? So it's a binary number that we're entering into my unary processing machine, right? And we're going to start with the tape head there at the 1. And so what happens, we start at state 0. It says if you see a 1, replace it with a 1 and go right. And now we are still at state 1. And what are our options? If we see a 1, we replace it with a 1 and go right. Well, I don't see a 1. If I see a lambda, replace it with lambda and go left. Well, I see a 0. There's no way to leave state 0 if I see a 0, right, on my tape, if my symbol is a 0. So that just means we fail. Done. Doesn't work. Now, drawing these Turing machines can be very time-consuming. And if you start by sitting down and just trying to write it using your wits, you may have some trouble. And so what you really should do when you're trying to write your own Turing machine, when you're trying to design a Turing machine, is you should start by writing out in English, what's my algorithm, right? So here's an algorithm for a Turing machine that will add 1 to a binary number. Let's just take a look and see what's going on here, right? And the first part of this algorithm is very, very similar to the first part of any algorithm you should write for most of your Turing machine problems, unless you have something very simple like what we've seen before. And the first step is always check the formatting of my string, right? So in the case of the unary number that we added 2 to, we kind of moved along making sure everything was a 1. That was the first step. We checked everything was a 1 until we got to a lambda, and then we backed up, right? And so often the first line of your Turing machine algorithm will check the formatting of the string, right? If I'm trying to have something that is of the form A star, B star, C star, then my first step may be move along making sure I have all A's, followed by all B's, followed by all C's, and then go back to the beginning and, well, I guess if I have A, B, C, if it's A star, B star, C star, I don't have to go back to the beginning. I could just say, all right, go to the end, make sure it's all of the right form, A's and B's and C's, right? On the other hand, if I want to check that the language, let's say A to the N, B to the N, C to the N, whether a string is in that language, right? So where N, language A to B, N, C to N, such that N is in the natural numbers. If I'm trying to see if my string is in there, then I do want to check the formatting, right? The first thing I want to do is I want to look and say, does it start with A's and then all B's and then all C's, and then I'll move back to the front and I'll start trying to figure out a way, how do I count how many A's I have and make sure I have the same number of B's and make sure I have the same number of C's. So the first step in many of your programs is going to just be a basic check, formatting of the string. Is it only A's, B's, and C's? There's no D's, there's no Q's, right? But all the A's come first, then all the B's, then all the C's. Okay? All right, so let's clean this up. There we go, and let's start again. So here's my algorithm to add 1 to a binary number. Okay? First thing I'm going to do is I'm going to move to the right, making sure the string is just 1s and 0s until I see a lambda. Okay? After that, I'm going to move to the left one cell. And in order to understand this algorithm, actually, what you need to understand is how to add 1 to a binary number. So remember, if I have a number like 1110 and I add 1 to that, then that's just 1111. That's easy. But if I have a number like 11101111 and I add 1 to that, well, what do I say? I say 1 plus 1 is 0, carry the 1. 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 1 plus 0, that's just 1, and then I can just copy the last few ones over, right? So the trick to note here is that we picked a problem that has a very easy method to add 1, right? Which is basically you scan along through the string until you see a 0 and change that to a 1. And if you get all the way to the end and there's no zeros, then you just change that lambda to a 1. Right? So that's how to add 1 to a binary number. If this isn't immediately obvious to you, pause the video, go mess around with adding 1 to binary numbers, review binary numbers, and then come back. Okay? Okay, so let's see. Can I just get rid of that? Beautiful. And so let's review again our algorithm for our Turing machine to add 1 to a binary number. We're going to start by checking the formatting, making sure it's just 1s and 0s. And then we're going to move left one cell, and then we're going to keep doing this, right? We'll have some sort of a loop. If the current cell contains a 1, write a 0 and move left, right? That's 1 plus 1 is 0, carry the 1, right? We're going to keep doing that, just like I explained, until the current cell contains a 0 or a lambda. As soon as we get to a 0 or a lambda, we will write the 1, and we will move left to the end of the string so that we're, well, to the start of the string, I suppose, and then halt, right? So let's take a look at a machine that does this. And here's the machine that does this. You can take a look and make sure it really does. We'll try it on an example in a minute. But state 0, I've actually kind of labeled these states according to what they do, right? So state 0 is the scan right to make sure the formatting is correct, right? And you can see that I'm going to keep moving to the right. I'm going to keep moving my tape head to the right. As long as I see a 0, just replace it with 0, move right. See a 1, replace it with a 1, move right. And so I'm going to keep looping around here as long as I see 0s and 1s until I see a lambda. If I see anything else, I see a 5, I see an A, I stop, I lose my string, I can't add 1 to it. It's not a correctly formatted binary number. But otherwise, when I see a lambda, I move the tape head to the left. And then we've got our state 1, which says turn all the 1s you see into 0s, right? So as long as I see a 1, turn it into a 0, right, and go left. Now if at some point I see a 0 or a lambda, right, then I need to put in my 1 and I'm pretty much done. If I see a 0, replace it with a 1, go left, and then I just need to keep going through all the 0s and 1s until I get to the start of my string. So state 2 is, I say here, you only get here if you're not at the far left of the string yet. So you keep going left until you see a lambda, Whereas if you get to state 1 and you see a lambda, right, which means that it was all 1s until I got here, then you just take this jump. You write your 1 to add 1 on the far left, you stay put, and you go to the halt state. Okay? So what I want you to do is I want you to kind of pause the video and just look at this Turing machine for a minute. Look over these instructions that I've got. There's our algorithm again, and make sure you really do understand what's going on here. We'll do one quick example or maybe two examples, but it's really important that you understand how we transitioned from here's my algorithm to here's my actual program, right? Here's how I designed my Turing machine. Okay, so I've moved the Turing machine up to the top of the page so that we can do this. Let's do a couple of examples. Let's do an example where the string doesn't match the format, right? So suppose we have, here's my tape. Of course, it's infinitely long. Suppose we have the string 1, 0, 2, 1, 8, right? And everything else is lambdas. We are going to start with my tape head at the start of my string. And we see a 1, place it with a 1 and go right. We're here, not a problem. We see a 0, replace it with a 0 and go right. But we get here, our tape head's pointing at a 2. And if you look, there is no transition out of state 0 that allows us to transition on a 2. So done, we fail. Okay, the machine just reports an error. All right. Let's try another example. That's a good example. Let's try adding, let's start with the binary number, let's see, let's start with binary number 3, right? So that's a 1 and a 1. And let's add 1 to that. So if we do the math on the side for a minute, 1, 1 plus 1, 1 plus 1 is 0, carry the 1, plus 1 is 0, carry the 1. We have 1, 0, 0, right, which is 4, so good. So 3 plus 1 is 4. So we'll start with our tape head just there on the left, and let's go. So we start at state 0, and I see a 1, so I leave it alone, right? I see a 1, I replace it with a 1. I'm just going to say leave it alone, and I move the tape head to the right. Again, I see a 1, I replace it with a 1, I move the tape head to the right. I'm still at state 0. Now I see a lambda, so the only transition I can take is this transition to state 1, which says if you see a lambda, leave it alone, move one step, move the tape head to the left. So tape head is back here on the left. Now I see a 1. As long as I see a 1, I'm going to replace it with a 0, right? As long as you see a 1, replace it with a 0 and move to the left. So I'm going to take my 1 and replace it with a 0 and move my tape head to the left. Right? And I'm still at state 1. I see another 1, replace it with a 0, move my tape head to the left. So I'll take my 1, replace it with a 0, move my tape head to the left. Now I see a lambda. And at state 1, if I see a lambda, it says write a 1 and then stay put and transition to halt. So I write a 1. I stay put, I go to halt, which means I'm done, I've succeeded, and indeed I added 1 to my binary number, which is kind of cool, right? I mean, come on, admit it. This is sort of vaguely cool, okay? Let's just try adding another 1 to the number 4. Let's do something sort of easy. If I have 1, 0, 0, and I add 1, and I'm in binary, I just get 101, right? No carries, no nothing. So let me try and shrink some of the stuff we've got already and do this example. Miraculously, for once, it worked. Sometimes the software works well and does what you want it to. Most of the time, it splits things up and is nasty, but that's fine. We're in good shape. So we want to start with the number 4 in binary on our tape, our infinite tape, right? 1, 0, 0. And we start with the tape head pointing at the beginning of our string. We go to our start state. It says if you see a 1, replace it with a 1 and move right, and if you see a 0, replace it with a 0, move right, and it stays 0 the whole time. So we see a 1, replace it with a 1, move right. See a 0, replace it with a 0, move right. See a 0, replace it with a 0, move right. Now we see a lambda on our tape, so I'm going to transition from 0 to 1, writing a lambda, leaving it alone, but moving the tape head left. So we're back here at the 0. Right? And now I'm in state 1. State 1 says, if you see a 0, replace it with a 1 and move left. So we're going to replace that with a 1 and move the tape head to the left. Right. Maybe I'll do my tape head in red now. There's my tape head. Okay. And now we just want to move back to the left side of the string. Why? Because that's what this problem decided to do. So we're in state 2. If we see a 0, write a 0, go left. If we see a 1, write a 1, go left. So I see a 0, leave it alone, move the tape head to the left. I see a 1, leave it alone, move the tape head to the left. Finally, I see a lambda. That tells me to move the tape head 1 spot to the right and transition to the halt state. So I end up with my tape head pointing at the first digit in the number 5. Hooray! So here's an interesting problem from the book. It says, construct a Turing machine that starts with the symbol pound in one cell, where all the other tape cells are blank. The beginning position of the tape head is not known. The machine should halt with the tape head pointing at the cell containing the pound, and with all the other tape cells being blank. Okay, so the idea here, let me just move this instructions a little bit out of the way, is that we've got, we have our infinite tape. And this is kind of a little bit different than what we normally do, right? Because I said, the only thing written on here is one pound sign, everything else is blank. Infinite tape. And we start with our tape head here, and all we want to do is find the pound sign. Okay? And of course, maybe you should pause for 1 second and think about how you might do this. So hopefully you've thought about it for a minute. The problem is, of course, that if I just say, well, if I see a lambda move to the right, then, that's fine, and I could keep doing that forever, and I'd never find the pound sign. In this case, if I see a lambda and go to the left, I'll find the pound sign. That's great, but if I started here and always went to the left, I'd be in trouble. So what I'm going to have to do is I'm going to have to kind of wiggle left and right, left and right, left and right. The trouble is, if I wiggle, I need to know, how do I know if I've seen one already, right? How do I know go 1 left and then maybe 2 right and then maybe 3 left and 4 right and so on, right? And so what I'm going to do is I'm going to say, what I'm going to try and do is build a Turing machine that does the following. Now we're not going to for this particular Turing machine check the formatting of the string, because this is kind of a different problem than we've been doing. But what I'm going to do is I'm going to follow this kind of process. I'm going to say, okay, when I'm looking at a spot on the tape, I'm going to either be going left or be going right. Let's start by going left, right? So if I see something that is blank on the tape, then I'm going to make a note that I've been here. So maybe I will just draw, maybe I'll draw an X on the tape, and I'll move the tape head 1 to the left. And if I don't see the pound sign yet, I'm going to try searching to the right. So what I'll do is I will write an X on the tape, and then I'm going to keep going to the right until I see a blank, right? Until I see a lambda. And when I get there, if I don't see the pound, I'll write an X, and then I will go to the left, until I see a blank. I'll write an X, and I'll go to the right until I see a blank. I'll write an X, I'll go to the left. Oh, look! I guess it's until I see a blank or a pound symbol. So now I've seen the pound symbol, right? But the instructions tell me the machine should halt with the tape head pointing at the cell containing pound. Good, with all the other tape cells being blank. So now what I got to do, I know I came at this tape at this from the left, or from the right, right? I headed left to get here. So what I need to do now is I need to kind of zoom along until I get to a lambda erasing everything, and then zoom back until I find my pound sign. So let's try and turn that into a Turing machine. All right, so let's clean this up a little bit. And let's see what we get. So what did I say I have to do? I have to start. And I need my start state, of course. And if I'm at state 1, let's stick the halt state down here. Of course, if I see a pound sign, then I'm going to replace it with a pound sign, stay put, and I'm done, right? But other than that, I'm going to have kind of alternate between moving left looking for the pound sign and moving right looking for the pound sign, right? So I'm going to have to move back and forth for a bit. So otherwise, the only other thing I could possibly see is a lambda. And if I see a lambda, I'm going to replace it with my x, and I'm going to move left, because that's what I said I was going to do. And I'll move left to state 2. And what I want to do here is kind of keep track. State 2 is going to be my state where I am moving to the left until I see a blank, until I see a lambda, and then replacing it with an x. So state 2, well, I guess it's until I see a lambda or a pound sign, right, is moving left while I'm looking. Maybe that's a good way for me to remember what state 2 is. Okay? So if I'm at state 2 and I see an x, I just want to leave it alone and keep going, right? So if I'm at state 2, see an x, I'm going to write the x again and go left. And if I'm at state 2 and I see a lambda, then I got to go to, then I got to write my x and continue on to, I guess we'll call it state 3, which will be the opposite of state 2, right? State 3 will be moving moving to the right looking for my thing, right? So state 3 will be moving to the right. So as soon as I see a lambda, I'm going to replace it with an x, and then I'm going to go to the right. And then while I'm in state 3, as long as I see an x, I'll replace it with an x and go right. And if I do see a lambda, I will replace it with an x and transition to state 2, which is my moving left. So this is great so far. Now I just need to deal with what happens if I actually see a pound sign, right? Eventually, hopefully, between 2 and 3, I'll be seeing a pound sign, okay? And I think I need to shrink this a bit, so let's see what we can do. Okay, so at this point, maybe we're in state 2, and we've seen the pound sign. Now, if I see the pound sign and I'm starting in state 2, that means I was moving to the left, right? So the pound sign is on the left, and all the other x's are on the right of that pound sign, right? So what I'm going to do, and maybe actually let's color this arrow red, only so that when I start writing more transitions on here, you can see what goes with what. So once I do see the pound sign, I'm going to replace it with the pound sign. I'm going to move my tape head to the right, and I'm going to go to this state, let's call it state 4. And state 4 is going to be clean the x's on the right of the pound sign. So state 4, I'm going to kind of have a loop, and whenever I see an x, I'm going to let's do that. I'll replace it with a lambda, and I'll go right. And I'll keep doing that until I finally see a lambda, right? And as soon as I see a lambda, I know I've hit the end of my x's. So as soon as I see a lambda, I will replace it with a lambda and go left. And finally, when I see my pound sign, I will replace it with a pound sign and stay put. Now, of course, there's another possibility when I find the pound sign, which is I found it in state 3, right? Let's change to purple. And if I was in state 3 when I found the pound sign, then I'm going to do the same kind of thing. Pound sign, replace it with a pound sign. And this time, if I'm in state 3, remember state 3 was I was moving to the right searching. So the pound sign is on the right of my x's, so I need to go left. And then state 5 is going to be kind of the opposite of state 4. As long as I see an x, I'm going, as long as I see an x, I'm going to replace it with a lambda and go to the left. And then once I get to the far left, as long as I see a lambda, I'm going to replace it with a lambda and go right. And finally, when I see my pound sign, I'll replace it with a pound sign and stay put. So this is pretty messy, and I encourage you to redraw this, turn off the program, pause the video, turn this off, try and reconstruct this without peeking. If you need to peek, great, peek. And I'm sure you can do it a lot more neatly than I can on this tiny iPad window, and I'm sure if I wanted to, I could redraw it beautifully. But I'll leave that to you. Sometimes the book asks for an answer that is not draw me a Turing machine, but actually just give me an algorithm that you could turn into a Turing machine, right? So for example, create a Turing machine that recognizes a to the n, b to the n, c to the n, and of course it should really say the strings of the form a to the n, b to the n, c to the n, such that n is in the natural numbers, but you knew that, right? So here's an informal algorithm, right? And this is something that we could turn into a Turing machine. So we start out with, if I'm pointing at lambda, I just halt, right? Because lambda's in this language. Otherwise, I need to check the formatting, right? And if the formatting is bad, then I just either move to a fail state or I just get stuck. There's nowhere I can go, right? But if I want to count how many A's, how many B's, how many C's I have, then maybe what I do, and now you can see kind of the technique that we had from before, right? If I have an A, what I'm going to do is I'll replace the A with an X, and then I'm going to move to the right, passing any A's and X's I have, until I see a B, and I'll replace that with a Y. So basically I'm matching them up. And then I'll go until I see a C, and I'll replace that with a Z, and then I'll repeat this by going back until I find the X and keep going, right? And so essentially, the idea behind this algorithm is if I have the string AA, BB, CC, then first I check, is this string in the right format, right? So do I have some A's and then some B's and then some C's? And if I do, then what I'm going to do is I'm going to say, all right, let me go here and replace this A with an X, and then zoom down until I see a B, and replace the B with a Y, and then zoom down until I see a C, and replace the C with a Z. So kind of matched up those A's, B's, and C's. And then zoom back left till I get to an A again. Right? I'm either going to get to an A or I'm going to zoom left and I'm going to find a lambda, right? So skip all the Z's, skip all the Y's, and skip the X's. I'll find an A, or I'll find lambda. So I found an A. So I'll cross out that A. And now I'll move to the right to see if there's a B. Oops, I didn't cross it out. I wrote an X, right? Move to the right to see a B, and I'll write a Y. And then I will move to the right and see if I see a C, which I do. So I'll write a Z, And then I'll move all the way to the left until I either see an A or lambda. Oh, look, there's a lambda. So now I got to check that everything to my right is all A's, B's, and X's, Y's, and Z's, because suppose we had more B's than A's, something might not be crossed out. But so I'm going to zoom to the right and say, oh, look at that. They're all X's and Y's and Z's. And I get to a lambda, so now I know I'm good. If I wasn't good, then I would just fail. And now what I'm going to do is go backwards and replace all my Z's with C's and my Y's with B's and my X's with A's. And I keep doing that until I get to a lambda, at which point I move one space to the right. And I'm pointing at the top of my string, and I transition to halt. Yeah. So this is a reasonable algorithm that kind of explains what's going on here, right? See? Scan right and make sure all the letters are now XYZ, because if anything's not XYZ, then we have a problem. Oh, and here I said if so, halt, if not, fail. You know, what we actually did is if so, we turned back X's into A's and Y's into B's and Z's into C's, and then we halted, right? But depends on what the problem is. Hopefully the problem is stated very, very clearly so you know what you're supposed to leave on the tape at the end. If not, you could just write down, here's what I'm assuming since the program doesn't say it, or since the assignment doesn't say it, or you can ask a question, right? Ask the professor if she leaves something out. So here's one last example. Construct a Turing machine to test for equality of two strings over the alphabet A, B, where the strings are separated by a cell containing a pound. Output 0 if the strings are not equal, and 1 if they are equal, right? So let's just talk about an algorithm to do this. I strongly encourage you to actually draw the Turing machine that does this, but if we just talk about an algorithm to do this, right? The first thing that we need to do is we need to scan the tape and make sure all the symbols are in the alphabet A, comma, B, comma, pound, right? Make sure all we see is A, comma, B, comma, pound, right? So scan the tape until we see a lambda, and make sure all the symbols are right, right? And then I guess we'll move back to the start of the string. Right? And of course we know we get to the start of the string because we move left until we see a lambda, and then we move right by one. And then we're going to do a very similar technique to what we did before, right? So what we'll do is, you know, if here's my string, my tape, infinitely long, and if I have a string like A, B, A, pound, A, B, A, then what I'll do is I'll start here at the left, and maybe I'll say, okay, let me check if that's an A. I'll change it maybe to a capital A, right? And then I will move to the right, skipping any lowercase letters in the pound sign. Well, skipping any lowercase letters until I see the pound sign. And then I will go to the right, skipping uppercase letters until I see the first letter. And if it's also an A, I will write a capital A. And I'll move left, past the pound sign, and then keep going until I see a capital letter. I'll move one to the right, I'll see the B, I'll turn it into a B. Are you with me here? So I've turned it into a B. And doom, 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 doom. I move to the right, and I try and match it. You with me? And back and forth, right? So we can kind of write this very informally before we turn it into a formal Turing machine. Look at first letter in the left. Oops, let's see, can I shrink this? There we go. Look at the first letter in the left string that is lowercase. Turn it to uppercase. Then scan to the right until the pound sign. Then scan to the right until a lowercase letter. And if it's the same as the one we just saw, how do we know that? Well, we're going to have different states. We're going to have to state where I'm scanning right and I just saw an A, so I'm scanning right, and I'm looking for an A, and a different state where I'm scanning right, and looking for a B, right? So the same as the one we just saw. So if it's the same we just saw, turn it into an uppercase. And then I guess we go back to 3. Right, go to the start of 3. And then, of course, we have kind of a and we repeat that until, so this is kind of a repeat, until there's no more letters in the first string, right? And then, right, and at any time it's until there's no more letters in the first string or we've already failed, right? If we fail, that's it, we're done, right? And then what do we got to do? We have to go back and change everything. So if it's all okay, oops, sorry, if it's all okay, which means we check to see that it's only uppercase now, then what we'll do is we will replace all uppercase with lambda, and finally write 0 on the tape. And I'm hoping it didn't tell us we had to write a 1 if they're not equal. Let's see, what did the problem say? Oh, that kind of sucks, but anyway, the problem said, oh yeah, I'll put a 1 if they're equal. So we got to fix this a little bit, right? If we fail, always good to check the problem when you're done, right? This is very good advice for homeworks and for tests. You know, if we fail, then replace everything with lambda and write a 1. Otherwise, we replace all uppercase, and I guess we're replacing all uppercases and the pound sign with lambda and write 0 on the tape. So again, you get the idea here. These are pretty complicated, and they're pretty complicated because we're writing real programs now, right? We're writing real algorithms to do things that about languages that are not context-free, about languages that are not regular, and to do things that we haven't done before, like, you know, this is much more in the lines of Mealy and Moore machines, but way more complicated, right? So you really just need to kind of take time and think about, how would I do this? This is a good time to read the book, look at the examples in the book, and go back and review the examples that I've given you here. Really, you know, the best thing to do is every time end up with a physical Turing machine, right? Draw the circles and arrows, and then you can really trace whether you've got stuff working or not working. And of course, the downside of me saying this is drawing these things is a lot of work. So I'm just going to wrap up this slide set with some facts to memorize, right? And this is kind of facts that you want to know for that party that you go to, right? Or for an exam, say. But the Turing machine that we're using is equivalent to a Turing machine that has a tape that's only infinite in one direction. You can say that you start with a string on the far left of your tape or something, and it's only infinite in one direction. You can still do everything you wanted to. You could also have a Turing machine that has lots of heads on it, right? So you have maybe one tape head and then another tape head that you can move independently. And the nice thing about that is then comparing, figuring out whether a string like A to the n, B to the n is in your language. Well, whether a string is in the language A to the n, B to the n is easier because you don't have to keep zooming back and forth to check everything, right? And it's also equivalent to a Turing machine with multiple heads and multiple tapes. So you can actually have multiple infinite tapes. You don't get any more power from having multiple infinite tapes, okay? And I'll just remind you, this is the Turing machine that we are using, right? The Turing machine that I've explained to you is the one we're going to use. I just want you to know, for future reference, that there are other models of a Turing machine out there, okay? So let's just talk for 1 second about what we've done here. We went from context-free languages to languages that are not context-free. We talked about how you could prove that a language is not context-free, and what you really should do right now is go watch the next video. Right? Go watch the next video. That would just be really good because that is a full proof that a language is not context-free using the Pumpinglemma for context-free languages. And then finally, we learned about the Turing machine. We learned about how you can use a Turing machine or how you can program a Turing machine, right? We really are talking programming now, in order to solve problems that are not context-free. And also to solve problems that are context-free and problems that are regular, right? Regular languages. But it's even more powerful than just regular or just context-free. It's like our PCs. It's like our Macs. All right? So, go watch the next video.